All right, guys. So in section 12.2, we've got really one new fractal that we are looking at, which is what's called the Sierpinski Gasket, sometimes referred to as the Sierpinski Triangle. In fact, we just saw that the chaos game that we played at the beginning of class actually turns into the Sierpinski Gasket or Sierpinski Triangle. We also looked at how to create the Sierpinski Triangle, starting with a triangle as well. In fact, we did that right on top of the chaos game that we had started. So let's go ahead and talk a little bit more about that Sierpinski Gasket and kind of some of the key features of it. So looking at this fractal, it is named after the Polish mathematician Wacław Sierpinski, who was alive from 1882 to 1969. So again, kind of like the Koch snowflake, a fairly recent discovery in terms of mathematical history. Now, just kind of like the Koch snowflake, we start with the solid triangle. And if you remember, that's what we did with the Koch snowflake as well. And then we have this recursive process where we repeatedly add smaller versions of the original triangle for the Koch snowflake, whereas we remove them for the Sierpinski gasket. So here's how you'd start. You'd start with a shaded in triangle ABC. Obviously ours were not shaded in, but they still gave us a good idea of how this works. We're going to call that the seed triangle. Next we saw that we removed a triangle which connected the midpoints of the sides of your seed triangle, which gives the shape consisting of basically three shaded triangles, each which is a half scale version of the seed and a hole in the middle where the triangle used to be. We're going to call that picture SG in terms of these slides. Once we do that again, notice that we get this picture right here. So again, for each of those solid triangles, we remove the center triangle from that, which now means that we have a total of 9 smaller triangles, each of them 1/4 the scale of the original seed triangle. As we continue to do that, by the time we get to step 3, we are now at 27 triangles. Each one of them is 1/8 the scale of the original triangle, and so on. As we continue to do that, we will eventually get to a point where, again, the figure becomes what we call visually stable. Remember, visually stable just basically means that at the point that you get to steps 4 and 5, there's no longer a way to distinguish it from one step to the next. Now, again, really the gasket obtained at step 7 is kind of where that is, but this is kind of what that looks like. Now, some interesting information. But first, let's go ahead and talk about the replacement rule. A very simple replacement rule. Start with your shaded seed triangle. Whenever you see a solid triangle, you replace it with a triangle with the middle triangle missing. Now, at first glance, you might think that the Sierpinski gasket is made up of a huge number of tiny triangles, but really that's an optical illusion. Theoretically, you would continue to remove those solid triangles until there weren't any more. In fact, if you were to continue to magnify any of these small specks around the triangle, you would just see more of the same, more specks surrounded by white triangles. Because of that, just like with the Koch curve, this Sierpinski gasket has self-similarity, which is all of the above. It is infinite, it is universal, and it is exact, just like the Koch snowflake. So again, magnification here, you can see that. Again, the infinite says that you could zoom in as many times as you wanted to, and it would continue to look the same depending on where you chose to do that at. The next is universal, so whether we zoomed in on this part of the Sierpinski triangle, or this part right here, or this part right here, it's going to look the same no matter where we zoom in. And the last is exact, meaning that as we continue to move in and zoom in at different levels, notice that the triangle looks the exact same at each of the different levels. Now here's where things get kind of interesting when you talk about perimeter and area. If you remember, the Koch snowflake had a fixed area, but had an infinite perimeter, which was kind of interesting. Now, the Sierpinski gasket should have an area then, but it actually turns out that that area becomes infinitesimally small, meaning that at each step you get smaller and smaller and smaller and smaller and smaller, and eventually it reaches a point at a limit where the area ends up being 0. So it's kind of interesting that at a certain point, obviously, again, as you go towards infinity, that the area actually is non-existent. However, at the same time, just like the Coke snowflake, the boundary continues to grow. As you continue to zoom in, the boundary continues to grow and actually is infinitely long. And so those are some interesting properties. To summarize those once again, your properties of their Sierpinski gasket, you have an exact and universal self-similarity, in fact, an infinite self-similarity as well. You have an infinitely long boundary, but zero area. So where is this useful? Because obviously, again, the point of this class is to show you some cool types of things which you would not see anywhere else, but actually are in the real world. Well, one actually kind of surprising example is that the Sierpinski gasket can be used to look at cell reception on your cell phone. In fact, a cell phone antenna that's efficient needs to have a large boundary, just like their Sierpinski gasket, and a very small area, because a smaller area means more energy efficiency. It also needs to have exact self-similarity, that way it works equally well at every frequency of the spectrum. And so, not surprisingly enough, the Sierpinski gasket is used as a model for that. In fact, not only in antennas, but are also now used in most cell phones as well, as in wireless modems, GPS receivers, and so on. The rest of the slides for 12.2 just talk you through the chaos game that we played earlier in class today. Feel free to read back through these and see those once again if you would like to. They do kind of detail that for you and also have some pictures to show you what it looks like after 50, 500, and 5,000 rolls in case you wanted to see that progression. But again, that was something we saw in class, so not necessarily something that we need to read over. One kind of surprising thing, obviously, that we talked about that might be worth noting, and if you did not write it down from the activity, this would be the slide to look at, would be that even though the chaos game is ruled by laws of chance, you kind of expect that it would be a random pattern of points on the triangle that you created, and instead getting an approximation to the Sierpinski gasket, which gets better the more that you play it. So, kind of an interesting thought, interesting idea if you wanted to copy it down. But again, we talked about that during class. Okay, so that is it for the Sierpinski gasket and obviously for the chaos game as well. Actually, in the next section, we'll look at what's called the twisted Sierpinski gasket, which is very similar, but does have some interesting applications for it. Until then, have a great rest of your day.